Okay, it's right at 2, so we're today start our today's seminar. Thank you everyone for joining here in person or online. So today we are very honored to have Professor Michael Beer, who is a professor and head of the Institute for Risk and Reliability, Leibniz University Hannover, Germany, to give us a presentation as part of our Lifeline public seminar. We have this public seminar usually once a month, and it's free and it's broadcast online. We have all this recorded video on our newly established YouTube channel. And we have the B-Jam. So if you miss that later, you can catch up online. So today our presentation is efficient reliability analysis with hybrid uncertainty. So Professor Michael Beer, as I introduced, he's a professor and head for the Institute of Risk and Reliability. He has so many achievements, and he's the editor-in-chief of ASME Journal Risk and Uncertainty in Engineering System Part A and also Part B. He's also editor-in-chief of and associate editor of many different journals. He's a chairman of the European Safety and Reliability Association, president-elected of the International Safety and Reliability Association, and a co-chair of Risk and Resilience Measurements Committee. Without further ado, I want to, Professor Beer, you all know him, and we have all the information online. You can check later. Without further ado, I want to have more time for Professor Michael Beer to bring us the wonderful seminar today. Okay. Thank you.
Thanks very much for the kind introduction and very warm welcome to my presentation. So I'm going to talk about efficient reliability analysis with imprecise probabilities. So efficient reliability analysis, I think you can imagine what this is about. Imprecise probabilities maybe is a bit vague, okay? So I will give a small introduction to that and then talk about these methods. So as you can see, there is a tank to quite a number of colleagues and collaborators, former PhD students, postdocs, and so on. So that is a work which has been for many years. So that is kind of a summary presentation, what we did over kind of 10 years and even more. All these people have contributed to this presentation, so I'm just giving a summary. This is not all my own work, okay? So, but basically my research area, my key research area since I graduated with a PhD is this area of imprecise probabilities. So that has spread and has been expanded over the past years. Also thanks to all these colleagues who have made quite key contributions to this area. So that seems to not go. I need to switch to the presentation, I think. Here. Okay. Yeah, okay. So let's look at the very big picture. So what we want to do as engineers with our actually big responsibility, not only for the community, but also for the society, we want to do a numerical modeling. And that numerical modeling is not only about the structure, but it's also about the interaction of the structure with the environment, with the society, and so on. So we have to solve a very big problem. And we want to come up with a prognosis which is reliable, which is trustworthy, and which is also efficient. It needs to be quick, okay? And that relates not only to the structural response, but it also is talking about hazards, safety, risk, robustness, economic impact, and so on. So we have to solve a very big problem. So solving a very big problem means we need to be numerically efficient. We need to have numerically efficient solutions to come up with results very quickly. At the same time, our results need to be close to reality, to be reliable, to be trustworthy, okay? And these two items are kind of in a counterbalance. If you model something more in detail, it is closer to reality, but not numerically efficient. If you want to do something numerically very efficient, you usually have a rough model, which is very fast, but not so close to reality. So we have to find the balance between these two items. And in particular, here we have a challenge, and that is the challenge of uncertainties, which is basically undermining this kind of problem. So dealing with uncertainties means our analysis is typically not very efficient. And if we have uncertainties, it's very difficult to find the result which is close to reality. So we have a third component in this kind of balance here. So how to deal with uncertainties? The ones you know, or the approach you know from your classes, is to deal with probabilistic methods, where you have a distribution function. So capture everything with a distribution function, find the distribution model, find the parameters, do your calculation, in reliability analysis, you come up with a precise number for the structural reliability or failure probability. Question is, how trustworthy is a single number when you know only a little about your input? So you don't know exactly what distribution function should I use? What is the parameter? You know only roughly. You still pick one model and come up with one number. Obviously, this does not really reflect reality. So we need to think about additional approaches which can match this kind of challenge of uncertainties. There are two pathways to go. One is to say, okay, I use a distribution of models. So I have another layer of a probabilistic model over the class of models, okay? So that is what we call subjective probability, which typically leads into a Bayesian approach, where you can update your models by way of some data, and then you find also a distribution of the result, in this case, a distribution function for the failure probability. So that is a pathway to process so-called epistemic uncertainties. But it needs some idea about how should I put this distribution of the models in the input, which is the prior knowledge, okay? If you don't have prior knowledge, or if you have your prior knowledge as in a very vague form that you say, okay, I cannot even put weights on my models in the input, subjective weights, which you need for this pathway, you can say, I just deal with a set of models. I have just bounds of the models, and I know I'm somewhere in between, but I have no understanding of how to put any kind of weights on these models. Just deal with a set of models. It's a different approach, no probability, okay? Then you end up with a set of results, basically a set or an interval of a failure probability. So with imprecise probabilities is the pathway on the right-hand side. So it's not dealing with precise probabilities, it's dealing with imprecise probabilities in a set-valued way with set-valued descriptors. So we have basically probabilistic models with set-valued descriptors in a parametric form, can also be in a non-parametric form, set-valued system descriptions, so that you deal with a set of models for the system, and this can be done in a parametric or non-parametric way. So, of course, we have developed methods which deliver bounding probabilities for events of interest. So your events of interest, failure probability, will then come up with some bounds as an interval. Of course, we cannot capture everything with a set. So there will always be something which is outside the set. So we can never be sure that we capture everything. So that means these sets come always in association with a kind of confidence level. So you have a set of models and you say, I'm 95% confident that I'm within the set. So that's the idea here, okay? So how to deal with this in a mathematical way? It's actually very simple. So probability boxes basically explain this in the most intuitive way, where we say we don't have one distribution function, but we have a set of distribution functions, and that set of distribution functions has bounding functions. Once we know these bounding functions, we can have any distribution between these bounds, an infinitely large set. And that is what a probability box is doing. And then we can say, okay, we want to go one step further because we don't really know how big is this set that we should capture. So if we ask 5 people to come up with a set for the same problem, they come up with different size of the set, okay? But we can capture this when we play with the size of the set and bring all this together in one model, use basically a probability box with a variable size. And that can be done with fuzzy probabilities. So that's just an instrument, basically, to deal with a set of probabilistic models. Very simple. So that means for the numerical processing, we can do very simple and very easy as well. Because when we pick one model out of the set, we can use the complete probabilistic framework for the analysis. And then, when we look over the range of the models, because we want to find the bounds of the result, then we use interval or fuzzy technologies to find the bounds. So that should be very simple. I stepped on the cable, maybe.
Yeah.
The problem. I'm too heavy. Okay, so let's talk about an interval. How to process these intervals? Because there is a lot of misunderstanding on this. But actually, solution very simple. Okay, that's an interval. It's something between A and B, or X left and X right. Nothing else. We don't know any additional information. Okay, so what people sometimes do is they say, okay, if we have an interval, we assign a uniform distribution based on maximum entropy principle. This sounds reasonable in the first shot. However, be careful. Each theorem has a background. Maximum entropy principle, the background is information theory, telling basically how much information is one value out of this interval giving you. Does this apply for our engineering cases? Sometimes yes, sometimes no. So if this, for example, is a value of a load on some structure, and you say, I don't know this load exactly, I just put it between A and B, and then you do a reliability analysis. Of course, you would, in order to get the largest failure probability, you would take the largest load, okay? If you go by uniform distribution, maximum entropy principle, you end up with a statistically averaged result, which would not give you the extreme case. And that can be devastating. If you design your structure according to the average, it may fail with a very large probability, and you don't know. So that case cannot be covered with information theory. However, if you put this as a prior distribution for a Bayesian update, then it's perfectly fine, okay? So it depends on the context. So in general, if we are dealing with intervals, we should be very careful to assign distribution functions, because the background for assigning the distribution functions must be satisfied by the physical problem, okay? Otherwise, it doesn't work. Because it could have, let's say, a single value behind, which is unknown. So actually, this is a Dirac function. If we dismodel with a uniform, it's completely wrong, okay? So we should be very, very careful with that. So in general, I would say, in order for processing intervals, we should be very careful with assigning distribution functions. We better not do that. Instead of this, we should say, okay, we use kind of an optimization procedure to find that value within the interval, which leads to the worst case of the result, okay? So then we say, okay, we cannot be sure that with this interval we capture everything. So we should play with the size of this interval. And what is the reason for that? So in engineering, we want to make decisions and conclusions. And the results we calculate help us to make these decisions and conclusions. But in engineering, we don't need to cover any case in our analysis. The main thing to make a decision is to understand our structure or system, how it works. In order to understand the behavior of our system, it is totally sufficient to play with the size of this interval to see how sensitive is the answer, the response, with respect to the size of the interval in the input. If it's not very sensitive, it doesn't matter very much if you have a result in the right order of magnitude, okay? If it's very sensitive, you should change your design. That means with our intervals, you don't need to capture everything. These intervals are confidence intervals. They come with a certain probability. And then you play with the size in order to capture these kind of sensitivities, okay? And an instrument to do that, to do the repeated interval analysis with the variable size of the interval is simply a fuzzy set, which is a kind of, which can be discretized as a set of intervals, nested intervals. So in that way, we can do a one-shot analysis and capture an interval with a variable size. So it makes things more efficient. So now you can imagine if you want to analyze a structure and you need to, let's say, do an interval analysis, which includes a kind of optimization in the interval to find the maximum and minimum of the response, that is an optimization procedure. So that in each analysis in this optimization procedure, in the reliability context, is a reliability analysis of the structure. So what we have is a stochastic analysis, which is the yellow box. We repeat the deterministic analysis in the Monte Carlo simulation. Then we play with the stochastic model. That means we need to repeat our stochastic analysis for one interval, okay? For one level of the interval. When we change the interval size, we need to repeat the interval analysis. difference in of a corner of this plate is more than 15 centimeters, it's failure, okay? So we do a Liouville expansion of the load field, and this depends on 4 interval parameters, theta 1, 2, 3, 4. So now you would say, okay, theta 1 is easy, largest value for theta 1, largest force, largest failure probability. But look at theta 2, this is in the denominator of a sine function. So this is a non-monotonic relationship between theta 2 and the force. So that means the worst value for theta 2 will be somewhere within the interval, okay? And the trick is then to find it automatically, because that is the big challenge here. So we have these 4 interval parameters plus Young's modulus plus the sheet thickness. So we have 6 interval parameters in total. So now what we do is the following. We have a 6-dimensional space in which we need to do this optimization. In order to have this representation, this graphical representation, we keep 5 parameters in the midpoint of the interval and let 1 vary, okay? So let the sheet thickness vary, let theta 1 vary, and these things. So we have the individual dependencies now, keep 5 in the point except 1. So then we say, okay, the orange line is the value of the operator norm. This is the deterministic optimization. Blue line is the failure probability depending on that parameter. This is actually what we want to have. And we want to find that parameter which maximizes the failure probability. So for 5 of these cases, we have a monotonic dependency. So the endpoint of the interval will maximize the failure probability. So this is easy to see. But here we have a non-monotonic problem, the dependence on this parameter in the sine function, okay? So we see that we want to have that theta 2 which maximizes the failure probability. So how to get it? We could repeat the reliability analysis, which would be very demanding. But what we can then do in order to solve this problem in a very efficient way is we only solve this deterministic optimization and calculate the orange value, which is the operator norm, depending on theta 2. So depending on theta 2, we do an optimization. Which value of theta 2 will maximize the operator norm? And this is automatically the same theta 2, which will maximize the failure probability. So we solve the optimization with the orange line, with the operator norm, to find theta 2, and then use this theta 2 for one-shot failure reliability analysis to solve our problem. So that is very efficient. So we see here a comparison with vertex method and with double loop. So double loop is the brute force method. So we see the results here, and we see the numerical effort, which is tremendous. So when we compare this with operator norm, you see this is more than an order of magnitude difference in the or gain in the numerical efficiency, and we still get a correct result. When we use vertex method, we get one result even wrong because we cannot identify the point inside the interval which maximizes the failure probability. Because vertex method only looks at the endpoints of the intervals. So that method with operator norm has a huge advantage. So it's numerically efficient and it can even identify internal points effectively. And that can also be done for larger structures. So here we have a reliability analysis of a multi-story building under earthquake excitation. So you see we have a large-scale finite element model here behind. We have, let's say, a realistic load case, modulated Clough-Penzian spectrum behind this earthquake excitation. And we have a total of 13 interval parameters in this problem. So we say we look at the interstory drift. We put a threshold for the interstory drift in order to identify what is failure. And then we calculate the failure probability for this case. So then we compare again with other methods. And we see in order to find the maximum and the minimum of the failure probability with operator norm theory, we need to call our finite element model only 3,500 times. When we solve this problem with more traditional methods like vertex or quasi-Monte Carlo, we need 5 million calls of a finite element model. So this is completely hopeless, okay? But 3,500 is possible. In particular, it's a sampling approach. So that means we can also do kind of parallel computing and that kind of stuff. I mean, it's related to this optimization problem. So we need to, let's say, parallelize the optimization, which is also not so easy, but it's possible to, let's say, do this in some way. Okay. So another method to resolve the problem is to use surrogates. So one way to use surrogates is to use intervening variables. Typically, it is relatively easy to solve these problems if we have a linear problem or we have a nearly linear problem. When I'm talking about linear problem now, means a linear relationship between the interval parameters and the failure probability. Okay. So if this is monotonic, it's also easy to solve. But I mean, okay, if monotonic is easier to solve, let's say, but if it's linear, it's very easy to solve. So because then we can use first order derivatives and first order Taylor expansion. So that's the idea, to start from a first order Taylor expansion, Pf, depending on theta. So this will work well if this relationship is nearly linear, okay? So what can we do? If we do sampling, if we estimate the failure probability by sampling, we can estimate the failure probability, and we can also estimate the first derivative of the failure probability with respect to the parameters. This information comes from the same sample with no additional effort. So we can estimate these things basically with one shot. So this is a theoretical equation. This is the estimation through sampling. So how can we now use these things? We can say we simply apply a first order Taylor expansion to the relationship Pf depending on theta. So this relationship can be nonlinear, which is the green line. So that means if we put a point theta and we do a Taylor expansion here, first order, we get the blue line. So what we now want to do is, this is actually an interval. Based on this result, we want to know what is the failure probability for this and for this point, which are the endpoints of the interval. So we would get these points on the blue line. If the green line is strongly nonlinear, this will be far away, okay? So that means for small scale uncertainties, it's okay. But if the intervals are a little bit larger and this is nonlinear, it's not so good. How can we now solve this problem? We solve this problem by removing the nonlinearity. We plot this function Pf depending on theta, not depending on theta, but depending on an auxiliary variable. And this is the intervening variable. And this intervening variable depends on theta. And now Q of theta takes out the nonlinearity so that Pf depending on Q becomes a nearly linear function. So the idea is to capture the nonlinearity in this equation Q of theta. And then plot Pf depending on Q in a linear way, and then do the Taylor expansion Pf depending on Q. In terms of Q, not in terms of theta. So that is basically the idea behind. Question is, how does Q look like? Here we borrow a concept from the people from optimization. So they typically use this kind of intervening variables to do optimization problems, to make them nearly linear, to use linear programming then to solve the optimization problem. So and typically what they use is kind of power type variable for these intervening variables. So if we use these power type variables, they have an exponent in the physical space, which is unknown, which we need to find. And then we say, okay, we want to represent the limit state surface or performance function here. We represent the performance function as a linear approximation in terms of these intervening variables. So we have then the exponent of x as one unknown for each of these functions. And we have these coefficients g for each of these variables to specify the slope. Okay, so how to find these two unknowns for each of the intervening variables? We say we pick one point in the physical space, x naught, and we say at this point x naught, the approximation and the original performance function need to have the same functional value. Then we say the first derivatives need to be the same, and the second derivatives need to be the same. We forget about the cross terms, and that gives us a sufficient number of coefficients. So we need to only 2n plus 1 coefficients or points to calculate in order to find these parameters for the intervening variables. Once we find them, we have a linear approximation of the limit state in terms of the intervening variable, which looks like this. if we implement or if we substitute the physical parameters, we have a nonlinear approximation to the nonlinear limit state, which is actually quite high quality usually. So, but then we can solve the whole problem in a linear way. So linear limit state surface means typically we can use kind of first order reliability method. So what does this mean? In order to use first order reliability method, everything needs to be Gaussian and linear. Linear is okay with our approximation. Gaussian, we don't know, we can have non-Gaussian problems. So we need to have a second step of transformation from non-Gaussian to Gaussian to solve the problem with kind of form in the sense of, let's say, standard normal space. So this transformation of non-Gaussian to Gaussian is also nonlinear in terms of the failure probability. So that means we can here use a second level of intervening variables which remove this nonlinearity. So here we borrow the concept of first order reliability method. We don't do first order reliability method. We just borrow the concept in order to find the shape of this second level of intervening variables. And when we use this approximation as a surrogate for the failure probability, which relates to the reliability index actually, we can use these equations. So, and then we find C as basically from the equations in order to identify the coordinates of the design point from first order reliability method. So this is not using first order reliability method. This is just finding the shape of the equation for the second level intervening variables to remove the nonlinearity from the transformation non-Gaussian to Gaussian. So all we do is find the three parameters of this transformation. That's it. If we have a case where everything is normal, this thing collapses in a very simple form because we don't have a nonlinearity here, everything linear fine. So that special case is included. And we can get all these things actually from our sample. We can estimate these values that we need for these intervening variables. So we just need still one sampling result to do everything. Okay. So how does this now work? Typically, we say, okay, we have now this as input parameter theta as a fuzzy set. So we cut out one level here. So we have one interval. So we have one parameter interval. When we play with this theta in the interval, we would get a set of distribution functions, or here PDFs. For each PDF, we would get a result for the failure probability. So when we move this, when we play within theta, we would then end up with a set of the failure probabilities, which gives one interval for the failure probabilities. So that is a multiple repetition of the reliability analysis. What we do with the intervening variables is different. So we simply pick the midpoint here of this interval, or of this uncertain variable theta. Use basically could be the midpoint of this interval. And this is what we use in order to do one-shot reliability analysis with the sampling method. Variance reducing sampling method. Can be line sampling, subset sampling, whatsoever. Okay? Important sampling, can use anything. Once we have this result, we end up with one result for the failure probability. So now we use this sample in order to estimate our intervening variables. Out of one sample, we can basically estimate everything in order to put up the surrogate for the failure probability. Once we have the surrogate, this tells us how PF depends on theta based on the surrogate. So that is a numerical approximation, which is easy to calculate. Once we know the surrogate, we can easily calculate what are the bounds. And that for any kind of level. So that is basically solving the whole problem with a one-shot sampling analysis for the reliability. So as demonstration for a very simple problem, so it's just a settlement problem. So we calculated displacement under a foundation, and we say random parameters are the load and two Young's modulus. Okay. So each one has two parameters. So we have three parameters which are random. Each one has two parameters for the distribution, and we model them in an imprecise way as intervals of fuzzy sets. So now we are in the area of geotechnical engineering, and that means that the uncertainties here are very large. So for example, when you look into the codes, they tell you that you have very, very large intervals in your geotechnical parameters. And we say, okay, what's happening if we use this large range for these geotechnical parameters here? So we have 6 of them. So what we do is, now it's stuck again.
Stuck?
Yeah.
Is it working?
Yeah, okay.
Okay.
So what? No, but we are. We moved one slide ahead.
Stuff in my slides. Yeah. Yeah. Oh, that's just.
Let's go backwards.
What?
Yeah, one more back. One more. Okay, good. Thanks.
Is it working
Okay.
from your end?
Yeah,
Oh,
okay.
okay.
So what we do now with the intervening variables is we pick the midpoints of these variables here, which are intervals. We do one-shot sampling, and in this case we used importance sampling with a sample size of 300 to solve the whole problem. Find the intervening variables and then approximate the result in this way. So based on the sample size of 300, we get now a result which covers basically a large range of imprecision of the intervals of the geotechnical parameters. So that means even for, so here you see the purple one is the true, let's say, true solution, the reference solution, and the yellow one is our approximation. So you see several orders of magnitude, and 14 orders of magnitude of the failure probability would come out when we use these parameters for the geotechnical parameters that you find in the codes, which is a huge range. But I mean, this is a result which is not useful for practical analysis because you get a huge range which doesn't tell you anything, but which tells you how sensitive the whole thing is. Now, the nice thing is that we get, even for this very, very large imprecision, we get the results almost precisely. So that is the power of this method. So we can use it for large structures with a demanding deterministic analysis because we need a very, very small sample size only, moderate nonlinearities, moderate dimensions, and a single failure mode. So it has everything, has some limitation, but it's very powerful if we have very large imprecision. Finally, another method, which is non-intrusive, also using a surrogate, is non-intrusive imprecise stochastic sampling. So this, the previous one was developed by Marcus Valdebenito mainly. This one was developed by Wei-Peng Fei. So that is non-intrusive imprecise stochastic sampling, which is based on an expansion of Monte Carlo simulation. So local extended Monte Carlo is doing the following. Should come back. So what we do is we pick one parameter vector, theta star, okay, out of the intervals, could be the midpoint, and we keep it, and we do one analysis, one sampling analysis to calculate the reliability with this one vector, okay? So then we say, okay, we want to find the surrogate which relates theta and pf. So we want to find a surrogate for this. In order to find it, we use our one-shot sampling result, and we put in a ratio between the PTFs. In the numerator, we have a PTF which depends on theta. In the denominator, we have the PTF depending on theta star, for which we have the result. So that means, based on this ratio, we get a relationship between PF and theta. So based on the one-shot sampling result. Then we can say, okay, if we go a little bit further away with this theta from this one, and we have nonlinearity, this approximation may not be very good. So we say, okay, we can expand this and say we do extended Monte Carlo, global extended Monte Carlo, and we say we also sample this parameter for the reference solution. So during our sampling result, we also sample this parameter. So you say now, okay, this is actually an interval, why sample it? The sampling is completely artificial, just to cover a certain range for theta for the reference solution. Later on, we will take the expectation of the result with respect to this theta and the distribution we used for the sampling to remove the influence of the sampling. So that is what we then do here, but it covers a certain range. So it becomes a little bit more insensitive with respect to larger intervals. So that method has then also been expanded using a Bayesian method, collaborative approximate Bayesian analysis and these things. So but this is the basic form. Unfortunately, the signs here are not very clear, but it's okay. So we use high-dimensional model representation then in order to combine these results with a series expansion of PF depending on theta. And this series expansion is based on high-dimensional model representation. So first we have the value which we calculate with a one-shot analysis. And then we have a sum of first order contributions to this PF, changing only one theta at a time, and then sum them up. Then we have the second order contributions, always only changing two thetas at a time. So separate basically the contributions, make them higher order, and clearly you can see you can cut the series at some point. So then we say, okay, we use these Monte Carlo schemes, local or global extended Monte Carlo, in order to estimate these parts that we need for this series expansion. So we only need to estimate the first and second order, basically. The rest is usually the influence so small that we don't need them. So we break down the complexity of the problem with this kind of analysis. And then the nice thing is, if we do global extended Monte Carlo, we can also use intervals for theta instead of having a distribution function. So these thetas can also be structural parameters. We sample them artificially and then take the expectation for the result. So with the global extended Monte Carlo, we can also deal with interval parameters as structural parameters. So all the components come from a single sampling-based reliability analysis, and it estimates the confidence bounds with a relatively small sample size. So this can then be expanded. So we extended this also combined with specific sampling schemes like line sampling and these things with active learning surrogates and all kinds of things which are fancy and which reduce the numerical effort even further. So, but this was the, let's say, basic concept to use this NIS method. So how does this now look like for an example? Let's say we calculate the reliability of this transmission tower, and we say we want to put the limit of the displacement as a failure criterion. Then we have several parameters which are imprecise. So 160 random parameters are involved here, 80 bar elements linear for static loads. And we have a total of, I think, 40 intervals, which are the expected values of A and Young's modulus of the corner bars. So then we do then we put the limit 6 centimeters as a failure criterion. So first thing what happens is we do a one-shot sampling, and then we estimate these terms for the high-dimensional model representation. So these terms in the high-dimensional model representation, they show the dependency of PF depending on one parameter at a time as the first-order terms, right? So and then we can see, when we estimate them, we can see how big is the influence of each parameter on the failure probability. So that means this gives a kind of sensitivity of PF with respect to theta, one by one. So that means there is a sensitivity analysis involved, so that we can see like this, which parameter has what kind of influence on the failure probability. So based on that kind of result, estimating just the first order terms, this is a sensitivity analysis in order for model order reduction. So here we would say, okay, 4 parameters is enough, the rest has almost no influence. So that means we don't need to do this for all the parameters, we only find the critical ones. And that reduces the numerical effort and the complexity even further. So that is a drastic reduction of numerical effort in the end. So with these 4 parameters, we can then go ahead and say, okay, we calculate the first order terms, and the first order terms are nonlinear surrogates for the dependency between PF and one theta at a time, and these are nonlinear because they involve this kind of ratio, which is a nonlinear relationship, a ratio between the PDFs, okay? So that is a nonlinear relationship, a nonlinear surrogate, which tells us by how much will PF change when I change one parameter at a time. On top, deviating from this result, which is the one-shot analysis. So this is the one-shot analysis. This is the first term in the series expansion, the constant one. These are the first order. And since it's a statistical method, we also get an error estimate. So this is the error for the estimation of these functions. That is 1 order of magnitude smaller than this one. So the error is actually pretty small. So this works well if the intervals are not very large. So, but of course, we can also use this for large-scale problems. So this was applied to solve the first NASA challenge problem. So this is a flight control problem, which covers, I think, 5 different disciplines. and 21 parameters which are not well known, some with distribution functions, some as intervals whatsoever. So we bring all this together with 8 limit states and try to solve the problem. Just based on the sample, there's a black box problem. You can just evaluate the sample and see which are the most critical parameters and so forth. And the parameters are given like this, which is a complete mess. So you see basically that some are intervals, some are distribution functions with intervals in the distribution function and all kinds of stuff, very large. So our analysis has shown that, okay, there's one parameter which has a very significant influence and some other parameters which have some influence. So we decided to use 6 of the parameters to process further in the NIS method. So here you see the first order terms in the series expansion, the nonlinear surrogates, PF depending on 1 theta at a time, including the red lines, which is the 95% confidence interval for these results. So basically our surrogates come even with a confidence interval. And then we see the second order terms changing 2 parameters at a time, so which is this, including the 95% confidence interval. So even for these kind of complex problems, which are strongly nonlinear, this method works quite well. Yet it's numerically more efficient. So compared to interval Monte Carlo, it reduces the numerical effort by 3 orders of magnitude. And it gets even better results. So when you see these bounds are quite a bit tighter than what we get from interval Monte Carlo. So we make advancement on the quality of the result plus significantly on the numerical effort. So the whole thing leads to, let's say, the conclusion that imprecise probabilities look very demanding, or a demanding challenge if we want to do an efficient analysis with it, because we have the additional layer of these intervals in the structural model and intervals or fuzzy sets in the distribution functions. So which really blows up the complexity of the problem. But there are kind of clever solutions to still solve the problem with a low numerical effort, which is only a little bit higher than the standard stochastic analysis, if we think about a clever solution of the problem with one of these approaches. So that can also use nonlinear and high-dimensional problems, and the whole thing is completely compatible with our stochastic approaches. So we can use our rich repository of stochastic analysis to combine with these approaches. So we can quantify epistemic uncertainty in a set theoretical way and process it, and let's say consider comprehensively this kind of imprecision in the results, in the analysis, to find bounds on the probabilities of the results. So we can identify sensitivities with respect to the imprecision of structural and stochastic models. So that helps to make our world a little bit better, to come up with a bit more realistic models, efficient numerical analysis, and then can also do, let's say, large-scale stuff, which is industry size, and improve design performance and reliability. So I hope that this topic was not too big to still understand a bit of the stuff. It was just an overview. So there were some references to some papers, so you can also email me if you like, or ask some questions, whatever you like, if you want to dig a little bit deeper in these areas. But I think it's important to understand the concepts first, to see that what kind of concepts are on the market, what could fit my problem, and then you can pick maybe 1 or 2 of them to look a little bit deeper into the theory. Thanks very much.
Thank you very much, Professor Michael Beer. So I think the students attend today, they're either master student or graduate PhD students. So a lot of our research are related with structural engineering or more like higher level. Some of them work on Lifeline infrastructure resilience or city resilience, but all of them are really highly related with uncertainty, because we are studying complex systems and they are nonlinear, they are uncertain, right? So let's see if we have any questions online. Questions on site. I will check online. I'm not sure whether we have the online, they can actually hear us or not. Probably we're having technical issues today, but any questions? Oh, actually they're saying it's okay for them. The volume is a little bit higher than usual. Yeah, I'm not sure whether we are. So online audience, if you can hear us, if you have any questions, you can also unmute yourself and talk, or type your question in the chat box. At the same time, we'll see if any questions here.
You just email me if you like. Also okay.
Yeah, I will share. Yeah, sure. Go ahead.
Professor Beer, thank you for your insightful presentation. I'm a PhD student from Southeast University.
Okay.
I really enjoyed your presentation as my research is focusing on the rest and the resilience of underground internals. However, as a student, I will use commercial softwares, such as Ansys or Abacus or Comstock. However, as I understand it, they are all we call non-intrusive methods, because these companies will not give us their underlying code.
Yes.
So, do you have any critical suggestions when I encounter such high emotional problems or nonlinear problems? Thank you.
So you can use your commercial software, because these methods, at least the last two, were non-intrusive. So you can connect. So you can connect it to a third-party software. Basically, for the optimization, you change the input parameters and you run it automatically. You read out the results, so you can do optimization. But that's basically sufficient to do this kind of stuff. Or for the one-shot sampling, it's the same thing. If you do Monte Carlo, you just put a parameter vector in the software, let it run, read out the result, and then you can proceed from there.
Thank you.
So that's why we actually really focus on the non-intrusive methods.
Thank you.
Any other questions? So I have a quick one. Okay, so I know you have a real trying to catch. So now we are artificial intelligence is very hot, right? Everyone is talking about it. How do you see artificial intelligence can help us better capture this kind of risk and uncertainty?
I think artificial intelligence can in particular help, or machine learning can in particular help for surrogate modeling. So that is a big area for surrogates. AI or machine learning is a big area for surrogates for these active learning methods and these things that can be very helpful.
Okay.
I would say this is the number one. May also help to solve the optimization problem.
Okay. So basically, like we are help them to the concept is just that we can use it to solve problems more efficiently.
Yeah.
Right.
Yeah.
Okay. Any other questions? See online. We don't see any questions. Know that. Let's thank you, Professor Michael Beer, again. And if you have any questions, you can either directly reach out to him or send us questions, and we'll help you to continue the conversation after.
Okay.
Thank you so much.
Thank you.
Okay, so we will end today's seminar. Thank you, everyone, for attending our seminar today. Bye-bye.